Very pleased to have our very own Patrick Sutton from our group upstairs in Milliken give us a talk on where things stand on the analysis of looking at LIGO and TAMA data jointly. Got your degree, I guess, in quantum gravity?
Close. Yeah, close enough. That's right.
Years ago?
University of Alberta.
Spent a few years with Sam Finn at Penn State, and he came to us. And when he came, he agreed to take on as primary responsibility seeing through the completion of this joint data analysis between TAMA and LIGO. And we're right at the point where we see the end of the tunnel, and we hope it's not a train. Okay.
Thanks, Albert. Okay, so good afternoon, everyone. As Albert said, I'm going to be talking about the joint search for gravitational wave bursts that's been going on between the LIGO collaboration and the Japanese TAMA collaboration. And of course, I'm speaking on behalf of the LIGO and TAMA collaborations. So the talk in brief outline goes like this. I'll say just a few words on the history of the LIGO-TAMA joint effort. And then I'll say just a few words, general comments on network analysis, some of the pros and cons that are involved that we should keep in mind when then viewing the rest of the talk. I'll say a little bit about the LIGO-TAMA network during the science run that we're analyzing the data from, the S2 science run. And then we'll get into the actual guts of the burst search. A few words on the target populations that we're aiming at and the goals of our search. The burst methodology will be where the technical detail of the talk lies. And then a few words on the current status and the outlook for the search. Finally, while I will spend most of my time talking about the LIGO-TAMA search for gravitational wave bursts, there's also a search for inspirals from the Milky Way and emission by particularly loud GRB during the S2 run that are also ongoing. And so as time allows, I'll say a few words about those at the end of the talk.
So those are also part of the joint collaboration?
Yes, they are.
They called up with 3 different groups, subgroups doing the analysis.
That's right. So I'm mainly involved with the untriggered bursts analysis, so that's what I'll comment on mainly. So, okay, the timeline of the LIGO-TAMA joint data analysis. TAMA is an old man on the block in terms of taking observation data with their interferometer. They took their first 1,000 hours of data in August of 2000, which is a very long time ago now in terms of my lifespan in gravitational wave science. LIGO caught up in 2002 with our first observation run, or the first science run, as we called it, S1. And it was shortly after the S1 run, actually at the GWDAW meeting in that December of that year, that the LIGO and TAMA collaboration signed what we call a memorandum of understanding for a joint analysis of their data, searching for gravitational wave transients. So the stated goal in the MOU is to work towards practical and optimized methods for doing coincidences between TAMA and LIGO. And of course, the unofficial goals would be things like fostering collaborative relationships between LIGO and TAMA, and generally developing expertise and infrastructure for doing this sort of collaborative search. So there are, as Albert said earlier, there are 3 searches that have actually come out of this MOU. There's the unmodeled gravitational wave burst search that I'll be talking about mainly. There's also a search for galactic neutron star binary inspiral signals and gravitational waves from a particularly nearby gamma ray burst that happened during the time period in question. Now, the actual burst search that I'm talking about began about a year and a half ago in summer 2003 after the S2 run. We'll see that it naturally tends to focus on gravitational wave bursts at high frequencies, around 1 kilohertz. That makes it complementary to the LIGO-only searches, which are searching at lower frequencies, down around a few hundred hertz. We hope to have the results cleared for release at the GWDAW conference in a few weeks in Annecy. And meanwhile, the other 2 searches, the inspiral and GRB analyses, are also in progress. They don't have plans for releasing results in the immediate future, though. So a few comments on collaborative searches. There are, of course, a number of different interferometer groups working across the world right now. LIGO, GEO, TAMA, and Virgo is commissioning their detector. Of course, there are about 5 or 6 bar detectors in operation. And so naturally one comes to the question of conducting collaborative searches for gravitational waves from these various, among these various groups. I think one can reasonably state that some of the advantages of doing these collaborative searches are that we can get more confident detection and a better understanding of detected signals when we work together Specifically, some of the particular advantages would be reduction in false alarm rates for gravitational wave detection, because you have extra detectors confirming your observations. With extra detectors looking at the sky, you have an increase in the observation time, better chances of getting lucky and seeing that rare event, or being on when the rare event happens. There are possibilities with more than 2 sites to extract sky direction and polarization information from your detectors. Massimo wrote a paper on that a few years ago that he gave a talk on that method, I think just a couple of weeks ago here. And then there are other advantages. Different detectors look at different parts of the sky. They may have sensitivity in different frequency bands, which gives you more coverage of that parameter. And then something that's not really commented on in the usual scientific literature, but I think is probably important, that the different projects all use independent hardware, they use independent software, independent techniques, and a lot of independent thinking. And that kind of heterogeneous mix helps minimize the chances that you would make some sort of subtle error in the analysis and that would lead to, for example, a false detection claim. Now, there are also cons to doing collaborative searches. We'll see a few of them as we go through this talk. Because you're looking at different parts of the sky and of different alignments, your different detectors see different polarizations, so, which means they see different gravitational wave signals. They're looking at different parts of the sky, so one of your detectors may miss a signal that the other one sees. If they're looking at different frequency bands, then they're seeing different parts of the gravitational wave signal. And all of that independence in hardware and software can make for a real headache then when comparing results. So we'll see a lot of these advantages and disadvantages in the context of this LIGO-TAMA burst analysis. Okay, so that's just a few comments on, yes?
Let me go back to just prior to that.
One more one.
The one where you talked about the advantages of different hardware, different software.
Right.
Which might be an advantage, but it might also be a disadvantage.
That's why you use the same words in both slides.
I think it's a 1-to-1. So
It's the same words.
right. So I don't have particular examples of where we've been caught out in the burst group on doing this, but I could suggest how other groups have had difficulties that might not be present in a joint analysis like this. For example, we have these subtle correlations in the data, 16 hertz and 4 hertz correlations that the continuous and stochastic searches turn up. And presumably that's something to do with the mechanics of how we collect the data. And presumably if we did a joint search like that with an independent collaboration, that's the sort of thing we may be better able to avoid, or at the very least.
But there's also the other side of it, which is that if one detector group, for example, made a terrible mistake and their timing was off by 3 minutes, so that all their events were time shifted by 3 minutes from everybody else in the world, you try to look for these things and demand coincidence among various detectors, you won't find.
Right.
Well, you might find it when you do your time shift analysis.
You might, if it's 3 minutes, or you might not.
Right.
So, it also goes the other way.
That's absolutely.
When you do this, you potentially miss things as well.
Sure. Of course, one way to see or to realize when you're doing something wrong may be to compare your results to another group, and it may help turn up mistakes that we make or our collaborators make, but that's speculation. Okay, so
It does suggest what we haven't done is doing correlated calibrations, for example, or injections,
right.
to pick up the kind of things you
But
suggest.
software injections have them.
Yes. But
But that's software.
with TAMA, yes.
You can even make a self-consistent mistake.
Right.
Right. Okay, so a few words then on collaborative searches. Now we'll get on to the detectors. Okay, so I guess I don't have to say a lot about LIGO to the Caltech JPL Association for Gravitational Wave Research, but for completeness, which is to say I made the slide for a public talk, and I'm going to use it. Okay, so LIGO, a flagship project in the National Science Foundation. Of course, it consists of 3 detectors at 2 geographically distinct sites. There's a 4-kilometer detector in Livingston, a 2-kilometer and a 4-kilometer detector in a common vacuum system in Washington State. We took our first science data, serious search data in the summer of 2002. The data that we're talking about for this analysis, this joint analysis, was collected about a year and a half ago in early 2003, our second science run. Since then, we've taken another 2 months worth of data that ended early this year with improved sensitivity, and the next run is planned for approximately a month-long period, starting probably in February of next year. The compulsory picture of the Hanford site, which I really rather like. I like the high desert. I think it's quite beautiful. The Livingston site, I'm not a fan of swamps, but it does have wonderful food and interesting wildlife. And okay, so serious information. This chart shows the progression of strain sensitivities over the first 3 science runs for the LIGO detectors. I suppose we're probably all fairly familiar with it. The important things to note are one, the nice progression from the first science run to the second science run to the third in their strain sensitivity. We're getting, at the end of the last science run, our 4-kilometer Hanford detector was very close to the design curve, and the sensitivities continue to improve, so that's really great news. And then the other thing that's important for this analysis is to note where the minima of these curves are. They're down around the 1 to 300 hertz region. And that's important because it's a different region from where TAMA has its best sensitivity. So the TAMA detector is a 300-meter interferometer. It's located just outside of Tokyo at the Mitaka campus of the National Astronomical Observatory of Japan. This is the corner station in this aerial photograph. You have one arm that goes due south and another arm that goes due west. The basic optical configuration of TAMA is the same as the original, or the LIGO-1 detectors. It's a recycled Fabry-Perot Michelson interferometer. As I said, the arm length is about 300 meters, and they began their observations in 1999. First long data taking was in 2000. So this is a picture of the inside of one of the sites, TAMA in particular. I had the privilege of visiting TAMA about a year ago and touring their facility. It's very nice. If you've never had a chance to visit LIGO or TAMA or one of these projects, I recommend you do it if you get the chance on a conference trip, for example. It's really fascinating to see how people who know things about machinery and can work with their hands, the sorts of instruments they can build. I'm rather useless in a physical laboratory setting, so strictly not allowed to touch anything in a place like this. You have your laser, the mode cleaner tube for TAMA. The beam is then fed into the beam splitter. You have the western arm and the southern arm, and then the output bench where the output signal is recorded, and the view down the west arm and the end station. So this shows the strain noise spectra for TAMA during their data taking run 7 and 8, which correspond to S1 and S2. So the scales here are different than on the previous plot. I'll show them together in a couple of minutes. The important thing to note is that their best sensitivities are down here around 1 to 2 kilohertz, which is quite a bit higher than the best sensitivities of LIGO, and that'll be important for a joint search. Okay, so how we actually look for gravitational wave bursts in this data. So the first thing is the target population. The basic reasoning here behind our search for gravitational wave bursts is that if you have a catastrophic event involving solar mass compact objects like neutron stars or black holes, then they can naturally emit gravitational wave bursts in the LIGO frequency band of a few hundred hertz to a few thousand hertz. And so some of the sample sources would be the core collapse supernova. This eye candy is a plot of various waveforms from different supernova collapses from the Zwerger-Mueller catalog. Also generally perturbed black holes if they're accreting or resulting from merger. Whatever engine powers gamma ray bursts is presumably strongly relativistic and could produce gravitational wave bursts. A new source that we're becoming interested in recently are cosmic string cusps, and presumably there are lots of other things that we haven't thought about that go bump in the night that could be emitters that we may be able to detect.
All the ones you've enumerated are currently being searched for by different subgroups of the burst group?
Right, so there is an externally triggered search specifically devoted to looking for bursts from events that are observed by other means, such as gamma ray bursters. The burst group itself routinely tests their sensitivities for supernova waveforms from the various catalogs for different merging black holes, the Lazarus waveforms at the moment. And we're ramping up to do simulations for the cosmic string cusps. There's also a dedicated search looking for cosmic string cusps based on matched filtering that's being developed at Milwaukee. That's being done by Javier Siemens, who in his previous life was a cosmic string theorist and now works with the with LIGO. So one thing that those different sources have in common is that for the most part, we don't have precise waveforms for them yet. And so this is the burst group mission is basically to be able to try to detect generic signals that don't have well-defined waveforms. So we can't base our search on having well-defined waveforms, which means optical filtering is out. So instead we develop techniques to generally be sensitive to excess power in the gravitational wave channel. And in particular, we focus on signals that are relatively short, typically less than 100 milliseconds. And of course, they have to have significant energy in our sensitive frequency band, or else there's no point in searching for them. Now, our goal here is to either if we can't detect anything, to at least put a rate an upper limit on the rate of detectable events. That's the scientific goal. And then the practical goal at this point is still to establish the methodology by which we do the searches, to develop our infrastructure and to validate the entire pipeline, because at the moment we don't expect to be able to see, realistically expect to see sources with our current sensitivities. So the basic procedure is outlined here on this slide. This is, in a few words, the entire LIGO burst search procedure. The two fundamental terms are highlighted: coincidence and blind analysis. So our burst search is based on coincidence fundamentally. We look for possible candidate events separately in each interferometer, and we demand that for them to be considered a gravitational wave burst, they have to be observed simultaneously by all of the detectors that are running. That's our current operating procedure, this basic principle. So in LIGO-TAMA, what that means is that each group, LIGO and TAMA, generates sets of these candidate gravitational wave events, which we call triggers. We exchange the triggers, and we look for coincidences between our interferometers. We also apply a few methods to help reduce the false alarm rate. In LIGO, we have a waveform consistency test that I'll describe a little bit later. And TAMA has some rather elaborate veto procedures to try to reduce their false alarm rate of fake events due to noise glitches in the instrument, for example. Once we've produced the trigger sets, we can also estimate the rate of accidental coincidences due to the false alarm rate by repeating the coincidence with artificial time lags added between the triggers from the various detectors. And we use fairly large time lags from between 5 and 115 seconds at the moment. And the reasoning there is that if a real gravitational wave burst comes through the Earth, of course it's going to have to be detected by the various sites in the space of a few milliseconds. It couldn't produce an event in one interferometer and then 5 seconds later produce a trigger in a separate interferometer. So any coincidences you get with these artificial time lags are just due to accidental background. Once you've collected your set of coincident events, you've estimated the false alarm rate, we can either declare, we can try to make a detection or claim an upper limit, and the basic procedure is to compare the number of coincidences that we get with the expected false alarm rate. And we have particular procedures that we use to work at the statistics. If we don't see any significant excess of events, coincidences, then we go ahead and set an upper limit on the rate of detectable bursts. The other key thing, besides your estimate of the rate of events, is your sensitivity. We estimate the sensitivity of the network using coordinated signal injection. So we add fake gravitational wave signals to the data from each detector and repeat the analysis and see if they actually produce coincidences in the output. And then the other very important point I wanted to make was that this analysis is a blind analysis, which is to say there are a lot of thresholds for generation of triggers, coincidence windows, and other tunable parameters in the analysis. And we set all of those numbers using two sets of data. One is a 10% subset of the full data set, which we call the playground. We analyze that and analyze it and analyze it again and again, tweaking our pipeline to get the best performance. And then we throw away that 10% of the data and analyze the remaining 90% to actually set our upper limits or make detections. And also, to get better tuning, we also use time-shifted data from the full data set. So we'll take the full collection of triggers and look at coincidences with artificial time lags inserted, so you know there are no gravitational waves involved, and do further tuning on that. And the whole idea here with this blind analysis is to avoid looking at the set of coincident triggers from which you'll derive your upper limits, because you want to avoid making potential bias in your statistical analysis of those events. Or worse yet, accidentally vetoing real coincident gravitational wave signals based on that you should have detected otherwise.
Has the artificially time-shifted 100% pass of the data been done?
Yes.
Do you see any difference between that and 10%?
No. Right. So that's a good consistency check. Right.
So the playground is represented in the full data set.
Yes. And that's not just for LIGO-TAMA, but I believe that's the same case for the LIGO-only analysis at lower frequencies. Yeah. So we haven't seen any reason to believe that the playground is inherently different from the full data set. Of course, if there was a difference between your 10% subset and the full data set, your error would then be to tune your pipeline in a non-optimal way. You'd be tuning it for best performance on non-representative data. It wouldn't actually be a mistake in your analysis. It would just be non-optimal analysis.
Why wouldn't we want to go away from the 10% subset
Right.
to 100% 1 second shift data analysis?
Right. A lot of people have been asking that question, and we made the decision in the Burst Telecon this morning to do that for our future analysis. We're going to be moving, in this case, this statement I made about using time-shifted data, this was done for LIGO-TAMA, but it wasn't done in the full, in the LIGO-only S2 analysis. But we're moving in that direction for the S3 analysis because we think we can get better statistics on the behavior of the data in an unbiased manner.
But then don't you have to be careful not to go and look at the single FO stuff? I mean, if you see something in the shifting data, you can't then go and say, okay, what is it in L1? Because then you're looking at...
Right. So there's, I think we have to be careful there, and I expect we're going to figure out exactly how we have to be careful with the S3 data. At the moment, the S3 data, the analysis of the third science run data is now being done in this manner. Currently using the 10% subset, and we're going to move to using the full time shifted data. And I think in a comparison of the two, we could probably, we'll probably have something to learn about how to do the tuning on the full data set without biasing ourselves by looking at single interferometers too closely.
Are there any idiosyncrasies that you require real physical coincidence of the data to flesh out? I think that's what you were asking.
Yeah.
Well, no, not just that. So in the Inspire group, we do time shifts using all the data. We do the time shifts, we use all the data in the time shifts, but we only look at the statistics of the coincident events.
Right.
We don't go and say, okay, there was a coincident event, what was it in L1 in the full data set?
Right.
Because then you're applying vetos on data, you're developing vetos on data, you're going to use the upper limit.
Right. So
you don't go in microscopically looking at what triggered the coincidence, the false coincidences?
Yeah.
Yeah, I think the logic would go like this. If you have two data streams, say the H1 and the L1, and say there's a real gravitational wave event that produces a signal in both, but say you've done a 5-second time shift of the data. So you'd have your real gravitational wave in H1, and then 5 seconds later the real trigger in H2, or in L1, sorry. But perhaps in the Livingston interferometer, maybe there was a noise glitch at this time, the 5-second time shift. So when you do your time shift analysis, you would call this a coincident event. And now your temptation is to take that coincident event and say, okay, can I somehow find a correlation with instrumental noise that I can use to veto this as a gravitational wave candidate? Because you know the two signals are not gravitational waves. Problem is one of the signals might be a gravitational wave. So you don't want to set up a veto procedure that kills this trigger. So you have to be careful not to look too closely at the individual detectors when you're tuning on time-shifted data. You want to do something that looks at the coincidence.
This isn't completely equivalent to the...
It's not equivalent exactly to the playground, that's right. In the playground, you include the zero lag coincidences and the non-zero lag coincidence.
So if there was an artifact where every time you see something, you see an echo.
Sure.
In the playground, you'd figure that out because you're looking at this stuff. Here, you would artificially prevent yourself from looking in great depth at what's going on and maybe miss the fact that you have echoes. Is that?
I suppose that's possible. Something to keep in mind is that you would expect the real gravitational wave signals in your data to be rare. So if you're doing things like tuning based on the statistical properties of large numbers of coincidences, then this chance coincidence with a real signal should not shift your veto procedure by much. So you're probably safe by doing this sort of tuning, but you want to keep in mind the possibility that there could be the odd trigger in your data that is from a real gravitational wave signal when you're doing time shifts. And so I think the lesson there is to only look at large classes of triggers.
I'm just worried that this restriction may lead you to, when you open the box and do the analysis,
Right.
you got a bunch of shit you didn't know what was going to happen because you didn't look at real coincident garbage.
Right, and I maintained that we should continue to include the 10% subset where we look at the zero lag coincidence, the real coincidence, and I think that was generally accepted in the burst group. Other people like it.
Do both.
Yeah. Okay, so right, so this is a schematic that shows the analysis pipeline graphically. So we have, in this case, 4 interferometers, TAMA and the 3 LIGO. The data comes out of them and passes through an event-triggered generation search code. So the TFC stands for TF clusters and POW for power. I'll discuss those in just a minute. We optionally add simulated signals to the data streams before they're analyzed. Once we've generated the triggers from the data set, these go into a coincidence. We look for coincidences between the detectors. We optionally add time delays so that we are studying, if we want to study accidental coincidences instead of real coincidences. Once they've passed through coincidence, we do a waveform consistency test on LIGO triggers, which I'll discuss again in a minute. And then we have the resulting coincidences that pass all the tests are our gravitational wave candidates. That's if we haven't added a time delay. If we do add a real time delay, then we're dealing with false alarms and not real gravitational wave coincidences. So there are some complications, though, to this standard burst analysis when we include TAMA. So I'm going to run through those over the next couple of slides. We have the physical differences between the LIGO and TAMA detectors. One is that their noise spectra are very different, as we saw earlier, and we'll see again. Another is that they're pointing in completely different directions on the sky, which is a small complication for doing coincidence. And then there are the technical problems that we use different search codes, different ways of characterizing the triggers that come out of the analysis, and so you have this sort of apples to oranges comparison problem. And I think these complications are present for any joint search between LIGO and TAMA, or at least any transient search, but I believe they're worse for the burst search, where we don't have good models for the waveforms or for the populations that we can use to try to combat these complications. So let's run through a couple of the differences. One is the alignment issue, antenna patterns. These plots show the energy or amplitude squared response of the Livingston and TAMA detectors as a function of sky position. So you have degrees east longitude here and north latitude on the vertical axis. So for example, if you're on the Greenwich prime meridian, at the equator, then the amplitude response of the TAMA detector is, I don't have a scale here, but say 0.5 out of a maximum. Whereas for LIGO, it's blue is low values, it's close to 0. Whereas in these red spots are where your detectors have the maximum sensitivity. So this is just to give you an idea of where the detectors are looking on the sky. You'll notice here in the Livingston plot, the red dots are the directions directly above and directly below the Livingston detector. This T marks the location of the TAMA detector. And it has best sensitivity directly overhead, over its own head, this red spot. And so what you see is that the TAMA detector is located very near a minimum of the LIGO sensitivity pattern. Whereas if we look at the TAMA sensitivity plot, here we see where Hanford and Livingston are. They're located almost dead in the minimum of the TAMA sensitivity. So there are two ways you could take this. One is that it's harder to do a coincidence search because they're looking in different directions, or you can be of the glass is half full variety and say, well, we've got good sky coverage with the network.
Chameleon mode.
I'm sorry? That's right. So this is the F plus squared plus F cross squared if you had equal power in uncorrelated polarizations. Right. So I just put this up to give you an idea of the alignments. Of course, for a specific signal with specific polarization and sky direction, you'd want to work out the antenna responses for that particular polarization for each detector. But the idea here is that basically we're looking in different directions. So since we're doing a coincidence analysis, everybody has to see the signal. We expect to be limited by the minimum of the antenna response. Although all other things being equal, well, for a given source coming from a given point on the sky, and then we have this waveform consistency test that does cross correlations. I'll discuss in a minute. The problem there is that TAMA and LIGO will see different polarization combinations. It's not clear yet how robust a cross-correlation between the two detectors would be, and therefore we are going to restrict the waveform consistency to cross-correlating the various LIGO detectors. This is an issue that's under study.
Who's studying it?
Laura, as frequently as I can harass her. Okay, so in the meantime, this is a simple experiment to give us an idea of the effect of the different orientations of the LIGO-TAMA detectors. So what I did is I did a Monte Carlo simulation of our Monte Carlo simulations. You take a blue curve here. This blue curve is meant to represent the sensitivity of any one detector, and we'll assume all 4 detectors in the network are identical. It's a sensitivity as a function of the signal amplitude in some arbitrary units. And then the vertical axis is the efficiency, the percentage chance of you detecting a signal as a function of its amplitude. And so you'd work this out for some particular reference waveform that you're interested in, or reference population. Now, if the blue curve here, as I said, represents the sensitivity of one detector for signals that are coming in from optimal position and optimal polarization, which is directly overhead and aligned with the detector arms. Now, if you then take that detector and you batter it with signals, linearly polarized signals coming from random sky positions, random polarizations, in general, you don't see the full amplitude of the signal. The antenna response is less than 1. And so you would expect your efficiency to be lower. And so this green curve represents the efficiency of the same detector when you average over all sky positions and all polarizations. And in general, we find that you lose about a factor of 3 in the amplitude sensitivity. And it's easy. We measure the amplitude sensitivity at the point where the efficiency is 50%. So you see there's about a factor of 3 difference between these curves. That's just from averaging over sky positions, going from optimal signal orientation to random. Now, consider 4 of these detectors, 2 pointing in the Hanford direction, 1 pointing as Livingston, and 1 pointing in the TAMA direction, and you repeat the analysis and see what's the efficiency for different combinations of the detectors, all seeing your given signal. And that's what the other 3 curves here represent. So, okay, so the red curve here is the LIGO triple coincidence detection efficiency. And then these 2 curves, the cyan and the purple, are for LIGO plus TAMA. The cyan is the 2 Hanford detectors plus TAMA seeing a signal, and then the purple is all 4 detectors seeing the signal. And I mean, one can argue about how big a difference there is between LIGO only and LIGO-TAMA. I would characterize this as a relatively small loss of efficiency. This is a factor of maybe 1.5 between LIGO's 50% efficiency amplitude and LIGO plus TAMA together.
Certainly not as great as you deduce from the picture.
Right. Right, which is telling you that the difference in alignments, at least in this simple model, you don't expect it to make a really big difference in the network sensitivity, not more than, say, a factor of 2. The exact behavior is going to depend on how identical your 4 detectors are and the particular signal that you're evaluating the efficiencies for. But I would argue, well, this gives you an idea of what to expect when you do the coincidence analysis. Okay, so the other important thing, besides the alignments, probably the more important thing are the noise spectra. LIGO and TAMA are not identical. This shows representative noise spectra for the various interferometers during the S2 data taking 8 run. So the LIGO curves are, I think, fairly familiar. The cyan curve here is TAMA. And the obvious thing from looking at this plot is that TAMA and LIGO have best sensitivity at very different parts of the frequency band. So LIGO is most sensitive down around a few hundred hertz, whereas TAMA has your best sensitivity up around 1 to 2 kilohertz. Now, if you want to have coincident detection of a signal by all of your detectors, that means they all have to be able to see the signal, and so your sensitivity is going to be limited by the worst detector at any given frequency. So I think that the logical way to conduct a search is to look at the envelope of your various noise spectra, and then to focus on the point where the envelope is a minimum. That's going to be the place where your network has the best joint sensitivity. And so in the case of LIGO-TAMA, it means that we're dealing with frequency range of approximately 700 hertz up to around 2,000 hertz. That's the area that we target for the production of of events, for searching for events. And by comparison, when LIGO conducts its own LIGO-only search on the same data, we restrict our attention to the frequency range from about 100 hertz up to about 1,000 hertz. And we allow a slight overlap between the two searches so we can compare them, and also in case there's a real signal that straddles the overlap region. So if I zoom in on the 700 to 2,000 hertz region, you can see the LIGO spectra in that frequency range are fairly well behaved. TAMA has a lot of structure here. I'm told these are due to the control system, but I don't know the precise nature of the structure. But what TAMA does when they produce their burst events is that instead of, they remove the lines by data conditioning and effectively focus their search on the frequencies that follow the noise floor of the spectrum. And if you do that, it's reasonable from this plot to expect that at the lowest end of the frequency range, the TAMA would probably be the limiting factor in the sensitivity, whereas at the higher frequency end, probably more comparable sensitivity between the various detectors. So just made that statement there. Okay, so once you've determined the noise spectra and the effect of the alignments, the other important thing in the search is how much data do you have to look at. So in the S2 data taking 8 run, these are the data totals for each individual detector. I think it's safe to say that the weak spot for the LIGO interferometers was the Livingston detector had a very poor duty cycle, which is blamed on the seismic environment. And so this limited the amount of data we had when all 3 LIGO detectors were on. By comparison, TAMA has a very good duty cycle, 81%. And that means that when we do a joint analysis, one possible way to conduct the analysis is to use TAMA as a substitute for Livingston during the times when the Livingston detector is not on. We can salvage more of our own LIGO data in analysis like that. So if you compute the times when you have your Hanford detectors on plus 1 of Livingston or TAMA, these are your totals. We wind up getting quadruple coincidence about 18% of the run, 250 hours. There's a small amount of time when Livingston is on, but TAMA is not. It's just a few hours. And then there's a very large amount of time. The largest single chunk of data is from the period when our Hanford instruments were on with their high duty cycle. So was TAMA, and Livingston was off. So in the burst search, we find that we need to have three detectors operating in coincidence to get a good low false alarm rate with reasonable thresholds. And so by this logic, we see that a LIGO-TAMA joint analysis makes this 325 extra hours of data available to us that would have been ignored if TAMA was not operating. And so I think one of the big benefits of doing a joint analysis like this is that we get a much larger increase in the observation time. In this case, we've more than doubled the observation time.
Patrick, that's interesting. If you
Yeah.
just assume that TAMA was running,
But if you multiply,
you predict over 57%, and it's
Yeah.
only 23%, so that must be that there's a substantial anti-correlation between, when we're up, they're likely not to be up?
wait, I'm not sure I see.
0.7
Not
times
too
0.8, right?
Yeah, 0.7 times 0.8 is 0.56. So we have 18 plus 23 is the total time that TAMA was up. Right, these are disjoint data sets. Yeah. Okay. So the big plus of doing a joint search in this case is that we more than double the data set that we have available to look for bursts. So we've got a better chance of getting lucky, and if we fail to see anything, we can at least get better rate upper limits. We can cut them in half versus what LIGO could do on its own. And somebody will ask the question, what about times when only one of the Hanford detectors was on? For example, these network combinations. It turns out because of the duty cycles and the behavior of the detectors that only a small amount of data was in these combinations, and it tended to be low quality, and so we left it out of the search. So we analyze H1, H2 plus 1 of Livingston or TAMA, or both of Livingston and TAMA as our data set. Okay, so how do we actually produce the gravitational wave burst candidate triggers? So there are 2 different search codes used, one for LIGO, one for TAMA. In the LIGO case, we use a routine called TF clusters due to Julien Sylvestre, who until recently was a postdoc here at Caltech. The basic idea, just schematically, we take the data from a single interferometer. It's run through some data conditioning routines to remove lines and whiten the data. And then it's passed into the TF clusters algorithm proper. The TF clusters algorithm constructs the time frequency spectrogram of the data, and then it compares the power level in each pixel of the time frequency plane to the expected value from background averaged over 5-minute time periods. And so it then thresholds on the amount of power in each pixel. And so you get this, what we call a black pixel map. Pixels that are black are above the threshold that are improbably loud compared to the background noise. And then the TF clusters routine looks for clusters of these pixels of some minimum size, and those are produced. Those are called the triggers that TF clusters produces. So once TF clusters has identified these time frequency regions that look like significant excess power, they're put to a parameter estimation algorithm, which estimates a duration, a bandwidth, frequency, signal to noise ratio, and those become the triggers that we then exchange with TAMA. And the one significant modification for use, or two significant modifications for use in the LIGO-TAMA analysis were, one, we tuned TF clusters to be sensitive to high frequency signals, which is to say we choose the time frequency resolution to be very short time scales. And then secondly, we only retain triggers that overlap the frequency band of interest, and we throw away any other triggers. Now, TAMA uses a technique that is similar in principle, but of course different in fine detail. They use an implementation of the excess power algorithm. Here's a reference. The basic idea is first that they do some data conditioning to get rid of lines. Again, they construct a spectrogram of their data, but they use a different clustering routine from TF clusters. So they construct the spectrogram normalized by the expected background measured over a half-hour time period. And then they sum over a fixed set of frequency bins at each time step, compute the signal-to-noise ratio for those in that fixed set of frequency bins, and declares a trigger if the signal-to-noise ratio exceeds some threshold. And then they go on to the next time segment in the spectrogram, repeat the procedure, and continue until you get to a time segment where there's no longer excess signal to noise. And then that period with the excess signal to noise is combined into a signal trigger, and they produce an estimate of the signal to noise ratio, duration, and time of the event.
Do you have any insight as to whether they're stationary on scales of half an hour?
I believe half an hour.
I thought that's what you said is the baseline.
That is the baseline by which they do the background estimation. I don't know. We would consider that to be a fairly long period of time in LIGO to try to estimate the background, at least with S2 data. Yeah. Okay, so so that's how they generate their triggers. TAMA uses also a collection of vetoes to try to get rid of triggers that don't match the gravitational wave signals they're looking for. They've put a fair amount of thought into veto generation. And so I'll just quickly run through the two schemes they use because they're fairly interesting. The first one's an intensity veto. This is similar to the types of vetoes that we look for in LIGO when we generate our triggers. So the basic idea is that they looked at their auxiliary channels and they observed that there are glitches in the light intensity in the power recycling cavity. And those glitches tend to correlate fairly well with trigger production from the gravitational wave data stream. And so they now, when they, I must have an automated transition time. So they look, when they produce an event from the gravitational wave data, they look to see if there's also an intensity glitch at the same time in the power recycling light intensity channel. And if there is, they throw away that trigger. They say it was caused by the glitch, by whatever caused the glitch in the light intensity. And so this plot shows the tests for this veto. The blue dots are on the horizontal axis the signal to noise ratio of the trigger from the gravitational wave channel, and then on the vertical axis, signal to noise of the corresponding time in the intensity channel, and you see there's a correlation. And so they set a threshold for declaring a veto and say, any trigger that has SNR in the intensity channel above this line is thrown away. And so this data here all of these triggers would be vetoed. They wind up eliminating something like half of their triggers in this way. They did safety checks by injecting in hardware, by actual shaking of their mirrors, various supernova waveforms, and this shows the green dots are the same data triggers but generated from the hardware injections. And so they observe that this appears to be a safe procedure. They set the threshold high enough that they don't kill any of their injected signals, so they believe this would be safe. It would not kill a real gravitational wave signal. And then the gray dots on the end here are the same as these triggers except sampled at 100 millisecond time offset, and they observe that triggers here that have a large intensity glitch tend not to be so large. The intensity is not so large 100 milliseconds before or after, and that's a sanity check basically, that your glitch is a short duration thing. The second veto they use is, this is really interesting. It's a time scale veto. We've never tried anything like this in LIGO. Part of the reasoning here is that in TAMA, they historically have not had anybody to do coincidence analysis with. So if you want to do a burst analysis and you want to get rid of your false alarms, you have to make up inventive veto schemes. We haven't had to do that in LIGO because we have 3 detectors we can do coincidence with. So Masaki Ando, who's their main burst person, came up with this procedure. The basic idea is to look at the time scale of the trigger and to veto it if it isn't short enough to be of the class of gravitational wave bursts that you're interested in. So the idea here is, sorry, I have to clear out transition times from these slides. So the basic idea here is that gravitational waves that we're looking for are of millisecond scale, say less than 100 milliseconds, whereas they observe that the noise in the interferometer tends to be of second or longer scale. And so what they do is for each trigger that comes out of the pipeline, they compute the mean power over approximately a second, and they compute this second order moment, basically the variability in the power over that second. Now, if it's a short duration signal, say a few milliseconds, then the variability of the power will be large because it's a low most of the time, and then it shoots up for a brief period and shuts off again. So injected signals tend to live, short duration injected signals tend to live over in this end of the space. And these dots actually represent injections of supernova waveforms. Whereas a noise glitch that tends to be on their second scale would be on the long duration end of this plot. And so what they do is they inject a bunch of they inject a bunch of simulated signals from families of interest. They figure out how far to the left the worst of these signals is, and they set a threshold there in the plane that's represented by this black curve. And then any trigger that comes out of their pipeline that's on the long side of that curve is thrown away. They're not saying it's not a gravitational wave necessarily. They're saying it's not the type of gravitational wave that we're looking for. It's not the short duration gravitational waves. So it's an interesting procedure, and it is used in the TAMA trigger production for this analysis. Okay, so false alarms, right. The next step, once we've generated the triggers, we do coincidence. We use simulations to tell us how accurately we can determine the time of arrival of a given signal, and we find we can do a lot better than 10 milliseconds. Whereas the time difference between the various sites, the distance in light travel time, is much larger than that. So for the LIGO detectors, 10 milliseconds, and LIGO-TAMA, you're talking about 20 or 30 milliseconds. And so when we do coincidence between LIGO and TAMA, we wind up requiring that events be seen by LIGO and TAMA at the same time up to approximately 30 milliseconds, and we add a 10 millisecond safety window just for safety. We repeat the coincidence by adding artificial time shifts. We can estimate the false alarm rates. Just to give you an idea of the order of magnitude we're talking about, for triple coincidence in LIGO, we typically aim for about 10 to the minus 6 hertz, which corresponds to about one event over the 2-month observation, over the science run that we've analyzed. Whereas for LIGO-TAMA, when you add in the 4th detector, we find that we naturally get false alarm rates that are a lot lower, down around a nanohertz. So you're talking something less than 1 per year accidental coincidences. And in fact, you can fairly easily get down to less than 1 false per century, based as estimated from this procedure. So that's another one of the benefits of doing the joint analysis. Okay, so I mentioned that LIGO does a waveform consistency test. I'll just run through it very briefly. The idea is to take the triggers, to look at the raw data from around the time of coincident triggers in LIGO and see if the waveforms are consistent in the different detectors. It's done by a cross-correlation test. So we take the data from one interferometer, normalize it, data from the other interferometer, normalize it, multiply and sum over an integration length. And this is the Pearson R statistic. You'll hear it referred to as the R statistic in LIGO talks. Basically what we find is that we take this R statistic, you compute the cross-correlation, you compare it to what you would expect just based on noise, without a correlated signal buried in the noise. And we find that we can get rid of about 99% of our false alarms in this way with a negligible loss in sensitivity to real injected signals. Also, in case you're wondering technical details, we allow for different time lags that correspond to the arrival time differences at the various interferometers, and we evaluate the R statistic for short duration signals, the sort we're interested in.
But that coefficient is never going to be 1.
The Pearson R, correct.
It will never be 1.
Right, yeah, that would be completely correlated, identical data.
That will never happen because there is grid.
Right.
And so if it's not 1, what can you infer that there is a distribution?
Right. So what you do is you compute the buildup of the R statistic over time as you integrate, and you compare that with how you would expect the cross correlation to build up if you just put in uncorrelated random noise, or more precisely, you take data from times of time-shifted coincidences, and you see how the correlation statistic builds up as you integrate over your 100 milliseconds or whatever length of data you use. And basically you do the actual engine underneath, I believe, is a Kolmogorov-Smirnov test, testing for consistency of the coincidence in the trigger, the cross-correlation in the coincident trigger to what you would expect from uncorrelated noise. And then you say the trigger passes, that it's correlated, if you fail the Kolmogorov-Smirnov test.
Do you do the Kolmogorov-Smirnov on a cumulative distribution?
I believe it's done by looking at the accumulation of cross-correlation as you integrate across.
For many events or for each event?
You do it individually for each event and compare to some threshold that you would expect for noise.
Now, your cartoon there suggests you can do this from all directions in the sky, but in practice you select only parallel coincident events, right?
I'm not sure I understand what you mean.
So you use Stanford and Livingston for this statistic because you don't want to allow for the kind of...
So what's important here is that the waveform has to look the same in the two detectors. If they saw very different waveforms, then you'd expect that it may fail, a real signal may fail the test. So it's important that your detectors be approximately aligned. If that's satisfied, it doesn't matter where the signal comes from, at least in principle. Pardon me. Okay, simulations, just be very brief. We need simulations to set our coincidence windows, to do all of the tuning, and to estimate the sensitivity of the pipeline. The procedure we use is that we actually make data files, frame files, that contain simulated signals of whatever population we're interested in. We share the data files with each other, and we run that, we add those simulated signals to our data streams. And the reason why I wanted to mention this is because procedurally it's very important. Actually exchanging streams of data with simulated signals is very effective at eliminating confusion when doing joint analyses. There have been other joint analyses conducted in which there has been exchange of signal parameters used to do coordinated simulations, which cause a lot of confusion when after weeks of trying to figure out what's wrong, people realize that they had a different definition of some parameter used. It can be a real pain in the butt. So I just wanted to point this out for anybody who's contemplating getting involved in something like this. Exchange of actual data frame files is the way to go. And in the actual waveform family we use for these simulations, very simple Gaussian modulated sinusoids, not because they're particularly realistic signals, but because they're really convenient and they're a standard that we use in tuning the LIGO analysis. So I don't have cleared LIGO-TAMA analysis results to show at this talk, so I will shamefully give you an example ripped from a GR17 talk from the burst group. This is the sort of stuff, this is the sort of information you get out of simulations. This is from the LIGO-only analysis of low-frequency data using a code called waveburst. It's a reference here if you're interested. These are the measured efficiency points for various simulated signals, and then a nice smooth fit, curve fit. You see the S1 result. So in the LIGO-TAMA analysis, we're using a different search code, but we expect the efficiency to be the same ballpark. And so if you read quickly, you can get an idea of the sort of range of amplitude sensitivities that we're looking at with the LIGO-TAMA search. If you want more complete details, you'll have to go to GWDAW in a month. Okay, so current status, as I said, we've opened the box, we've done the full analysis, our simulations, the coincidence, the false alarm estimates. We've computed upper limits or confidence intervals, and now we're doing checks on the results before we actually publicly release them, and we hope to show them in a few weeks at GWDAW. In the meantime, I can show you what one might expect as the result if we don't make a detection. And I won't commit to not having made a detection. Just stands in the room, and he won't allow me to do anything like that. Okay, so expected upper limits. For the different networks, the 3 network combinations, we have the 3 observation times in days. If you have no detections and you have a very low background, the statistical procedure we use is by Feldman and Cousins. It gives you an upper limit at 90% confidence that's just 2.44 divided by your observation time. So if you just take the observation time for each network and plug it in here, you get the expected rate upper limits. And if you combine the observation time from all 3 data sets, it's 20 days. Then the division is even easier, and it turns out that you'd expect an upper limit around 0.12 events per day. So for comparison, if we didn't have TAMA for this joint analysis, then the best we could do would be to combine this data set and this data set, which is a little less than half the total. And so we'd expect a LIGO-only upper limit. That's about a factor of 2 worse. And then,
This is at very large signal strength.
yes, so this would be for signals where your efficiency is 100%. Right. By comparison, before we feel too mighty, the IGEC, International Gravitational Event Collaboration, that operates bar detectors, they've got over a year of observation time, and so their upper limits are much better than ours. And we're just going to have to run for a lot longer to be able to get down to this level. But operating in collaboration with TAMA, with other groups, we can get down to that level a lot faster. Okay, so summary then, we have the LIGO-TAMA collaborations are conducting a joint burst search for gravitational waves seen in the S2 or DT8 data set from about a year and a half ago. It's in the late stages now. We've basically computed our results, and we hope to present them in a few weeks at ANSI. There are costs and benefits to doing this sort of collaborative search. So I'll just remind you, we have obvious benefits, things like reduction in false alarm rate by doing coincidence with extra detectors. We've got more observation time because we have more detectors watching the sky. There is some loss in sensitivity. We saw some plots earlier. I don't think the loss in sensitivity is too great in this case. And then there are the technical hurdles that make the analysis physically difficult to do. But again, I believe that my experience from this collaboration has been that it's been a worthwhile effort. I think the benefits from our collaborative search definitely outweigh the costs. So the obvious question is, what's the next step? We're looking at the possibility of a joint S3 search. That's from the data from earlier this year between LIGO and TAMA. There are also searches going on already between LIGO and GEO, or analysis of data between LIGO and GEO from that data set from earlier this year. And in fact, there are other collaborative analyses starting up between LIGO and the bar detector group, or RIGA, for example. But it's still up in the air whether or not LIGO and TAMA will do an S3 joint search. We'll be discussing that at the meeting in a few weeks. Some of the things, besides the obvious benefits that we've already seen, I think the natural next extension of a LIGO-TAMA joint search would be to implement something like Massimo's method for extracting polarization and sky direction information. That's one of the things that you can do with LIGO and TAMA that you just cannot do with LIGO alone because you don't have a third detector site.
But you need an event.
But you need an event first, right? I mean, you can develop the method based on simulated signals and be ready for when the real event comes along. You definitely don't want to implement it. You don't want to be in the situation where you're first implementing it after seeing an event.
Yeah. But I mean, this method actually, the way it can be used is actually to discriminate.
Mm-hmm.
A little signal against fluctuations
Right.
you see in detectors.
Yeah.
So it not only gives you possible directions and waves amplitudes, but actually confirms or disproves
Right.
your hypothesis that you have
Right.
detector.
Right.
So it could be used exactly parallelly on top of what we have done so
Right.
far.
Yeah.
Just to
Right.
So would it be
And so-
a second stage, or would it be a detector?
I think you do it as a second stage, like the waveform consistency test that we do in LIGO.
It's like the coherence
Consistency
as well.
check.
Right, and so physically, what would have to change in the LIGO-TAMA analysis is that we'd have to do exchanging fairly large amounts of raw data between the detector groups so that we can test the procedure, tune it, and make sure that it works.
Now,
Yeah.
we had a code we used for generating those plots and that code.
Right. Fortran, wasn't
The
it?
only thing we needed in order to be used from real data was to remove the routine that was simulating the business and get the inputs from the detector. I don't have that version anymore. I think Jack does.
Yeah.
I have a version that could be modified, made it work on the real data.
Right. I should mention the burst group itself has a guy, Malik Rachmanoff at the University of Florida, who is implementing this method for use in the LIGO burst search using LIGO-GEO or LIGO and some other detector. So he's setting up the sort of infrastructure for doing that. To actually implement it in a real search, we'd have to exchange data with the other group and do simulations and tuning. I just pointed out as an obvious further development of a collaborative search, is because what we've done so far has been fairly simple, basically a very simple coincidence analysis. And so that's someplace we could go for a little more sophistication in the future. So I see we're 5 after the hour. Questions took me a little later than I wanted. I guess if you guys have questions, I will hit you actually with one more slide. In case anybody's curious, I forgot I wanted to mention current status of LIGO. Yeah. I must have missed that talk. LIGO commissioning is continuing. There's been further improvements in the Hanford H1 sensitivity. Livingston, they've implemented this active seismic isolation system, HEPI, which is having dramatic effect. In particular, the interferometer stayed locked when a train passed through a couple of weeks ago, which is, if you've ever done one of these graveyard shifts at Livingston, is an amazing event, because when a train runs by the interferometer, it would knock the interferometer completely out of commission for about 45 minutes. And this would happen twice a night, in the dead of night, when otherwise everything is very quiet. So it's an hour and a half of your best data that gets killed every night like clockwork by these trains. And the ability to stay on when a train's rumbling by is, it's unheard of now for us. So this is great. This promises for an increased duty cycle for future runs, which will help us, again, get more observation data. And I know that Tom is also working on noise reduction right now.
Kuroda told me in October when I saw him at
Yeah.
Virgo that they've got a spectrum that's about a factor of 10 better on the right side of their...
High frequency?
Yeah, they're dropping the low frequency
Right.
down. They've got another decade.
That's quite a lot. Okay. I haven't seen that spectra, but I would like to see it. And then, as I said, LIGO's planning an observation run starting in February of next year. TAMA intends to be operational by that time as well. So there's the possibility of more joint observation data being collected. And then we have the longer S5 run for LIGO sometime later in the year. And the big news out of LIGO is the National Science Board has approved advanced LIGO. So that's not near-term effect.